here, and he's going to talk about variable order fractional diffusion equation. I'm really waiting for this talk. Okay.
Thank you. Thanks for the invitation and for the opportunity to speak at this workshop. It's a pity that I cannot be present offline, because I feel it's much better format, but sometimes things happen this way. I'm happy that I'll be able to present a talk on fractional diffusion of variable order and anomalous aggregation phenomenon, a work which was inspired in a discussion with Bruno Tuaudu, who is my co-author, on a previous work and observations that were done by Sergei Fedotov, who had an excellent and very illustrative talk yesterday on the matter. To be fair, my curiosity was more on the mathematical side and the fact that one could link such fractional diffusion equations, so to say, and pathwise properties of stochastic processes. And this really made me interested whether one can make some classical fluctuation theory results in stochastic processes work for the study of some of these equations and the properties such as, let's say, the aggregation phenomenon. And what I'm going to be very brief about, because I saw that most of the people are much better specialists on the topic than me, but I'll still browse through some of the model we have. So the setting is the following. We have some particle that would have a free motion m, provided there are no obstacles in the environment. However, there are some traps that are able to fixate the particle for a random period of time, and so that the particle really does not follow the free motion m. And one way to introduce this trapping mathematically is through a time change. So you take the initial free motion m, you subject it to a suitable time change L, and your motion in this environment with porous media or obstacles or traps is represented by the process X. A picture of this, which I simulated on MATLAB, which is probably the best I can do, is a Brownian motion that starts at time 0 at the green dot, ends at time 1 at the red dot. And you see that along the movement, which is upwards, there are a lot of places where it stays constant, basically. These are the positions where it has been trapped for some period of time. And this is precisely what I have described on the previous slide, and is, of course, very well known in this community. And what can be the objective then of a couple of mathematicians that would like to study this problem? The first would be to derive integro-differential equations or fractional equations regarding observables of this time change process m. So we would wish to study or derive some equations that are solved by expectations that you see in the first bullet point. This would link the time change process to a particular analytical object. And the second aim we had, and which I'm going to focus on in this talk, is to study the strength of the trapping, in the sense that if you have a process L, which describes the trapping of the particle along its movement, what kind of process it has to be, what strength they should have, the trap, so that they fundamentally alter the behavior of the free motion. For example, you would have a diffusion, which, if it is suitably time changed, maybe it preserves the diffusive behavior, but if the trapping is too strong, then the diffusive behavior is really so much changed that actually the particle starts to aggregate in bounded regions in space, which is certainly not the case if you were to have a diffusive behavior. So I'm going to speak about these two things, but Bruno has already said a few words on the first bullet point, and my intention is to focus on the second, because I really would like to emphasize how one can use classical growth and fluctuation results to attack a problem like this. So how would we, strictly speaking, proceed to introduce this time change? We have the free motion m, and then we have an increasing process sigma, which consists only of jumps represented by delta sigma. And the sizes of these jumps represent the times of the trapping the particle would be subject to. So what we have is we have to take the right inverse of this increasing process, and the right inverse is going to serve as the time change of our free motion m, and then we would have a process x which incorporates in itself a potential trapping effects. I would like to note that if sigma is increasing that by jump type process, then L has levels of constancies, and these levels of constancies are representing the respective traps and their length. A typical example for for such increasing process sigma is the classical subordinator, which is a very well-known process. It has non-decreasing paths, and it has two fundamental properties which are very clear, which are related to Levy processes. It has stationary and independent increments, which you can see mathematically defined in the bullet points 1 and 2. And if we were to have such a process, then all the information about its behavior is coded in its Laplace transform, which I have taken at logarithmic level. And it has the form of minus dl and a well-known integral with respect to a measure nu. The measure nu basically measures the intensity and the types of the jumps the Levy process or the subordinator may have, whereas the drift term d in our talk will be 0, and it's just a linear function that is increasing, and that's why it has to be greater or equal than 0. So if one were to take such a process sigma, which is, let's say, independent of some free motion, one can easily construct time-changed processes which are representing some kind of trapping. And one of the first works I'm aware of is of a colleague of mine, Emilia Bajlekova, from our institute in Bulgaria, back in 2000, where she studied the following problem, or at least it is equivalent to the following problem. You have a Brownian motion, which represents the free motion, and you have an independent of it, alpha stable subordinator sigma with fixed index of stability alpha, and then you construct B taken at the right inverse of this stable subordinator. This time change process is connected to the well-known fractional equation, fractional in time, dt alpha, and then we have the classical Laplacian to the right. And you can connect this process to this equation and proceed to study it. Studies in such direction of time change processes have been, up to my knowledge, quite extensive, especially in the case when the free motion m is independent of sigma. Let's say sigma is some subordinator, and then you can study the expectations of the process x via some integro-differential equations. As far as I learned from Bruno on Monday, there have been also results that go beyond that. I will say briefly in the next slides, in the case when m and sigma are not independent. But what is characteristic for the case when m and sigma are independent is that the trapping is homogeneous in space, simply because the subordinator really doesn't care where the free motion is, and it really imposes the same traps and the same strength of the traps everywhere in the space. So you basically see no difference in this path with respect to the potential traps in it. So what we studied with Bruno is a case where we took a couple m sigma, the free motion m, and the potential process for time change sigma, which is a couple is a failure process with respect to some filtration f. And we assume that sigma is Markov additive process in the sense that the future of m and sigma with respect to some information contained in this sigma algebra f of d, where v is the current moment in time, is really the future is predetermined by the knowledge of the position of m. So it is suffices to know m of v, and then the future probabilistically is predetermined by this knowledge of m. In this case, the sigma is a Markov additive process, and this has been extensively studied back in time. Even we used the work of Zinwer, which dates back from 1973. Actually, in his case, the potential form of sigma is more general than I'm presenting on the second line. But in our case, we have opted for the case when the conditional Laplace transform of sigma, conditional on the path of the free motion. So we are interested in the Laplace transform of sigma v, and we can have information about this Laplace transform conditional on the path that the free motion has taken up to time v. And in this case, this Laplace transform is known to be of the form that you see in the next two expressions, where in the exponent, what you see is really this typical term for the classical subordinators. But instead of one measure here, we have a measure which is accumulation of a family of measures and depends on the path of the process MW. So basically what we have in the first bullet point is described. We have a family of Levy measures, which is indexed by the space X. And really, this family of measures describes or allows for different strengths of trapping at different locations in the space. And what happens is the particle takes a certain trajectory, certain path. The potential trappings are reflected in the violet integral through this integration, which also can be reduced to the occupation measure of each position in the space, which is determined also by the, of course, by the free motion M. So if we were to have M independent of sigma, as you see in the third bullet point, then the violet integral would be simply the classical subordinator, because then it would be just V times mu dh. And then the position really does not affect the intensity and the sizes of the jumps, where here in the violet integral, we have this potential dependency. And the first question which we investigated is really to link such processes, M sigma, and then time change to X, which is X is M L of t, is to understand their expectations and link them to a certain fractional differential equation. So what we have is that we have some family of operators Pt, which act on function u, which is typically a C0 function. And this Pt of u is nothing else but the classical expectations of the process at time t. And we have shown that this PTU is a mild solution to a certain integro-differential equation, which you see on the screen with initial value condition u. G is the generator of M, but I have not taken any opportunity to define it because we shall need it. We shall not need it in the future. And nu bar is the tail of the Levy measure. Bruno has spoken about this briefly. I'm just going to mention, and I just would like to say that we have a route to prove that actually the solution is classical, but the work was already very voluminous, and we were happy to leave it with the link we established through the mild solutions. But as far as I understood, now there are more general results, and there is some advancement in this direction. What I'm going to focus about is the second problem, and I'm going to follow the paper. We didn't do this for the general free motion and general family of subordinators, but we have the following model. We have a Brownian motion, which will be the free motion, and the trapping effects are going to be modeled by a family of Levy measures. The family of Levy measures, nu dhx, everything occurs in one dimension, is actually a family of alpha x stable subordinators. So for every position in space X, we have a number in 0, 1 coded by the function alpha, such that nu dhx has basically the Levy measure of alpha x stable subordinator. Of course, this does not make our process sigma in any case stable subordinator, but its behavior is of course linked to the properties of the stable subordinators. And in this case, our equation that we have established on the previous slide for the time change process X, really corresponds to a variable order diffusion, and the variable order is in the space. I think this was yesterday's mu in the talk of Sergei Fedotov, Professor Sergei Fedotov. And this is the equation it corresponds to, but our utilization of this equation stops here. I would like to present how we can study the trapping effects for such process X, in which case, for what profile of alpha, we could have trapping effects for this process X, and for which we may not have. So for this purpose, I'm going to say present some assumptions on the profile or the function alpha, which describes the strength of the traps throughout the space R. First of all, we assume that alpha has limits at plus and minus infinity, but this is non-binding condition, but makes easier the exposition. And this limit is in 0, 1, alpha plus minus infinity. Next, we assume that alpha has a global minimum attained at least at one point, and it is alpha star. We denote this minimum. And third is not as an assumption, but as a notation, we introduce the sets A beta, which are all positions in space X, for which the strength of the paths alpha X is at most at beta distance from the minimum. Why? Why the minimum alpha star is the important quantity? Because the smaller the index of stability, the heavier the tail of the stable subordinator. So if there were to have some traps that really significantly change the Brownian motion in its behavior, this has to be seen at the level, at the positions where the traps are strongest, and they are strongest when we are close to the minimum of alpha star. That's why we have separated the set A beta, and A0 will be the subset of R for which actually the minimum is attained. So alpha X is alpha star. On the next slide, I'm going to present two possible profiles for alpha. One of them is a continuous function, which you see on the as a red graph, and alpha star is attained at a single point, this tip you see here. Then A beta for small beta is this set because it, let's say, captures all this part of the curve alpha, and then away from it, the values of alpha are at least beta distance from the minimum alpha star. This is quite a general profile one might have, and it's not very binding, but the second profile I'm going to look at is the next one. And in the next profile of alpha, the minimum is attained on an interval or potential union of intervals, and it is attained by a jump. You see that here A0 is A beta for all beta small enough, and then this minimum is really attained discontinuously, not in a continuous matter. This somehow plays a role in one of our results. This second profile, when you really have a bottom, clear flat bottom, but the bottom you really achieve by a jump, not continuous. And then we have the next general theory in our work. So if 2 times the minimum of alpha star is less than the minimum of alpha plus minus infinity, then, and beta is positive, is such that the Lebesgue measure of A beta is finite, then the average time the process Fxs, the time change process, spends in A beta is actually converging to 1 almost surely. So what we have is we have some kind of ergodic behavior, as far as I understand it, maybe not the right term, but what it means is that on average, the process can be found in the sets A beta for any beta small enough. So it really tends to stay at overwhelming proportion of time close to the minimum alpha star, or positions whose strength is close to the strength of the highest strength, which is alpha star. And it is curious to examine where these two comes from, but it will become obvious. But this is really a behavior about the whole path. What happens if we wish to ask whether we can find xt for a particular position in time for large t close to the maximum? And then we have such a result that this probability converges to 1, that the probability of finding the particle at the maximum, near the maximum trapping effects, we can prove it only in the case when we had the second profile for alpha, when alpha star is at bottom, which is discontinuous. So A beta equals A0 for some beta, and it is union of intervals. I don't know whether this is a deficiency of our methodology or it is a phenomenon that occurs, but I have to say that a similar phenomenon I have observed in another colleague of mine who has worked with two Italian colleagues of his in urn models, where they also have some dominant colors for the balls in the urns, and there the dominance is also described by some function alpha. I'm speaking very general fashion, and the strength of this, the colors that are dominant, their strength has to be also continuously, discontinuously attained, so that you have similar result that x of t is really from the dominant color. I don't know whether this link is superficial, whether it is technical deficiency, but we have to have this. And next, I'll be spending some minutes on how we can prove such a result. So roughly what we are going to do, sigma is measuring the trapping effect. So we are going to split sigma in two parts, sigma 1 and sigma 2, where sigma 1 measures the trapping that is forced on the particle close to the minimum alpha star, and sigma 2 is going to measure the trapping effects away from the minimum alpha star. Then we are going to approximate sigma 1 and sigma 2 with stable subordinators, and we are going to use growth estimates for subordinators and to determine the dominant one. This is the overall strategy, but it is too technical to achieve, albeit not too difficult. But it is rather technical. So I'm going to illustrate this on the very simple case where alpha x is alpha 1 when the Brownian motion is 0, 1, and alpha x is alpha 2 when the Brownian motion is away from 0, 1. So this is a much simpler case, but it's a very illustrative prototype. So what happens in this case, your Brownian motion starts from here. If it happens to be between 0 and 1, you see the strength of the traps through these high jumps, lengths of constancies, and when it's away from 0, 1, then it basically has almost a free motion. This means that alpha 1 is significantly smaller than alpha 2. And on this picture, we can see that we can easily isolate the two effects by considering when the Brownian motion is 0, 1 and when it is away from 0, 1. And then sigma v is really split up in two possible streams. One of them is accumulating jumps through the case when the Brownian motion is 0, 1, and accumulating trapping effects through the case when the Brownian motion is away from 0, 1. However, in the first red case, sigma is actually alpha 1 stable process because there the trappings are following alpha 1 stability. But the time is not deterministic, it is random time, and it is the occupation time, the time that the Brownian motion has spent in 0v. So this is what is the difference, is that the time is now random and it depends on the free motion. And the remaining proportion of time v minus h of v is actually attributed to a sigma alpha 2 stable process. So what happens in picture, your motion starts, I don't know why it's not hiding here, this thing. So what happens, I'm not sure it's visible at the top. What happens is your motion, the free motion moves, and when it is away from 0, 1, it is a gray curve, and when it is 0, 1, it is a red curve. And then the trapping effects are accumulated to the right through gray or red curve. And you see that on the y-axis, on the t-axis, is the time that the time scale of x, and on the x-axis or w-axis is the time scale of m. So the total amount of time that x spent in 0, 1 is actually attributed or accumulated through the red curve, and potentially the jump between the dot you see and the undershoot. This is the last term. So the last term, t minus the undershoot, can happen through the red curve or through the gray curve. But before this, we accumulate jumps through the red or through the red curve here on this picture. So it is a very clear way how, in this case, you accumulate the trapping effects. And if you measure the average time the process has spent in 0, 1, without looking at the whole slide, this is simply the cumulative time in the red curve, or the alpha-1 stable subordinator, was potentially jumping across T for the sigma subordinator through a jump of the alpha-1 stable subordinator, or the process has been at 0, 1, divided by the total amount of time T, which is simply the accumulation of all trapping effects, potentially through the red or the gray curve. And achieving some, doing some algebraic manipulations, dividing by sigma alpha-1, we see that this to converge to 1 means that sigma alpha-1 at the bottom has to be the dominant process. This is something quite natural. And how one can prove this? It's interesting that one can use really classical fluctuation theory and growth results for subordinators to really establish this thing without any appeal to equations. First
Mladen,
of all,
sorry,
yes?
Mladen, you've got around 2 minutes.
Okay, I'll finish the first part, and then who is interested can look at the other problem if I have been slow. I'll be finishing on only this, the average behavior. So the logarithm of the occupation time is roughly 1/2 logarithm V on almost sure scale. The logarithm of the alpha stable process is 1/2 logarithm V on almost sure scale. And respectively, the logarithmic behavior of sigma alpha-1 at time the occupation measure is 1/2, where 2 comes from alpha-1 logarithm of V, and the other is 1/2 alpha-2 logarithm of V. This means that this 2 times alpha-1 is the smaller than alpha-2, then the dominant behavior comes through the alpha-1 stable subordinator, and one can verify with some technical arguments that this limit is indeed 1. Since I have no time, I'm just going to mention what happens here. The process X is in 0, 1 at time t if sigma crosses time t through a jump of the alpha-1 stable process. This is what we have. And to study this, we have to really understand when is it possible that at time t, this is really here is the time scale of x, when this jump here is done really by a red curve, by the alpha-1 stable process. And it is a curious property of the alpha-1 stable process. When they cross across t, they cannot be close to t. And this, together with the other results we have established, and a lot of computations show that actually when 2 times alpha-1 is smaller than alpha-2, then the probability finding the particle in 0, 1 is converging to 1. But this topic presentation will be online. It is in the paper. I don't want to go above the limited, the time I allocated for my talk. Thank you very much for your attention.
Okay, thank you, Mladen, for interesting talk. And well, that was question.
Hi, Xiaochuan Yang from Brunel University. So thank you very much for the talk. Very interesting talk. So I have many questions, but I guess I'll only ask one. You mentioned this result of Saint-Lars about the Markov additive process and Levy system. So there, the formula you gave seemed to suggest that your process is a stationary M, but you are using Brownian motion, right, in all your results?
Yes, we use the Brownian motion in all our results because in all the results I presented, only one thing really is well understood for Brownian motion, this behavior of the occupation measure. We have attempted to generalize this result for much larger class through analytical means and less usage of fluctuation theory, but we have failed. That's the reason we are using Brownian motion, really.
Yeah.
We really cannot make it work, especially for the second problem, if we have more general process than the Brownian one. If I understood the question correctly.
Yeah, okay. So yeah, I was talking about this formula you gave about the Saint-Lars definition of MEF. Maybe previous page. Yeah. Yes. So you make a shift of a magnitude V.
Yes.
Okay, so I understood that this seemed to say that M is stationary. Is this the case or not?
No, the free motion is not stationary in principle, like the Brownian motion. I mean,
has stationary increments, I guess. It allowed the situation.
Not really. One can put more general Markovian, and this will be reflected here in this M of V that somehow suggests that we have dependence on the current position, for example. But we have used processes with stationary increments, yes.
All right.
Maybe I misunderstood the question, but I think it can be a general Markov process. And
so, for instance, a stable process should be fine, right?
Yeah, certainly, it is absolutely fine. And we have attempted to do some of the aggregation thing for stable, but our technique betrays us. Yeah, this can be much more than stable, but stable is an excellent example of stable as the next step.
Okay. Okay. Thank you very much. I'll send you a message. Maybe we can talk offline.
I'll be happy. Yes. Thank you very much.
Okay, right.
Hello, thanks for the talk. I have two very quick questions. One is if you have an idea on how you could approximate this alpha x, so this space-dependent coefficient from the discrete to the continuum, like thinking of a random wall that approximates to the Brownian motion, how you should, let's say, change the waiting time of the random walk according to having in the macroscopic limit this alpha x in the time derivative?
To be absolutely fair, I have not thought about this question, and I shall start to speculate without having any depth. So I really have not thought about this. I mean, I think one can approach such problems easily for random walks because it's much easier the space there. But how one would take the limit to Brownian motion, I really don't see it at the moment, sorry.
Okay, no problem. And the second question, if you can comment about conservation of mass of these equations, like, is it the case that there is conservation of mass or?
I think yes.
Sorry?
I think yes, yes.
Okay, thank you.
Right, I've got actually questions. You mentioned the connection of variable order fractional equation with reinforced urn model with dominant color. So it's just connection or just equivalent problems?
That's I have not been able to establish whether it's mathematically that's the same problem. But when you start choosing the same color, let's say you may think you're in a trap until you choose something else. But mathematically, we have not established it. This is a young colleague of mine who presented this work relatively recently, and I just spotted that they have the same technical problems. And I have briefly thought about this, and probably the connection is that when you start choosing the same color, this is as if you are trapped. But I have not established any mathematical question, a link other than this observation that one could think about intuitively about this. But it's interesting that they really have the same, I would not say a problem, the same phenomenon. They cannot prove this thing if you approach them, in their case, the maximum continuously, in our case, the minimum continuously.
Yeah, it's interesting connection.
I just wanted to broaden the picture because I think it's curious link.
Okay, Mladen, thank you again.
Thank you once again for your invitation. And thanks.